All right, welcome back, you guys. We're going to look at integration by parts today. So this is just another integration technique, and it can be applied to a wide variety of functions, particularly these types that we could not do before. So a little bit of development, so you don't think that this kind of came out of nowhere. If you remember, you remember the old product rule, right? Derivative of the u times v is the derivative of the first times the second, at least this is how I remember it, plus the first and then the derivative of the second, right? Well, if we integrate this, okay, and I'll just integrate like that here, then we would have uv equals, and I'm integrating this with respect to x. Over here, I'm integrating this with respect to x. Okay, see how that canceling for us over here? There's a cancels, and so you have another form for the integration of u dv. This is what I want. I'm going to put this in a different form. I'm going to solve for that. So let me subtract this to the other side. And so I have the integration of u dv is uv minus the integration of v du. And so I can break up, what I can do is it helps me to break up things like this and make it, or use this technique called the integration by parts. Okay, so this is my integration by parts. The integration of u dv is the same as uv minus the integration of v du. So it expresses the original integral in terms of another integral. Okay, so you kind of have to just see it, I think. So let's go ahead and apply this formula or technique, if you will. So what you want to do is you want to, actually let me come up here. You want to let dv typically be the most complicated portion that fits a basic integration rule. That's kind of the general form. And you're just going to be doing a lot of trial and error when you first try this. Okay, and then number 2, guideline, try letting u be the portion whose derivative is a function simpler than u. Okay. So if I'm over here and I'm looking at this first one, x e to the x, I would let my my dv on this thing be that e to the x dx, because I have a rule, basic rule. It's the more complicated part, but I can still have a basic integration rule for it. And so I'm looking for this is how we're going to set it up. I'm looking for who is dv. So I'm going to try that being dv, which means my u will just be the x. Okay, so I'm setting up, that's my u part. Okay, and let's see if this works for us. If it doesn't, then I'll change it up. Okay, so I'm going to go to the side. I'm going to let my dv be e to the x dx, and I'm going to let my u just be the x. Okay, and I'm going to run my integral. Well, the integral of 1 dv is just v. Right? I'm integrating 1 with respect to v. Don't worry about the plus c part. We'll take care of that at the end of this. And now I'm integrating e to the x. Remember, the integral of a to the x is 1 over ln of a. So 1 over ln of e in this place, in this instance, and then e to the x. Right? And we know ln of e is just 1. So we just end up with v being e to the x. Okay? Now let's go over here to the u. If u equals x, then du dx equals 1. But let's take the dx to the other side. So du equals 1 dx. And now let's do the integration by parts. So here's number 1. We're going to go to the side and identify u and dv. And number 2, let's write the formula for integration by parts. The integration of u dv is u v minus the integration of v du. Okay? So in other words, the integration of x e to the x dx, remember this is the u, and this was our dv. Oops. This was our dv. Is. So the integration of u dv is uv. So u is x. V is e to the x. There's our u times v. Minus the integration of v. Here's our v, e to the x. And du. What's du? dx. Okay. So the integration of x e to the x dx is x e to the x minus, now I just got to integrate e to the x, which we know is 1 over ln e to the x plus a constant. So the integration of x e to the x is x e to the x minus e to the x plus c by integration by parts. Now we could check that, right? We could check it by taking the derivative. Right, if we took the derivative of x e to the x minus e to the x plus c, right, we would get derivative of the first, derivative of x is 1, derivative of the first times the second plus the first, derivative of the second, minus derivative of e to the x is ln of e to the x, derivative of 0 is that. And so we end up with e to the x plus x e to the x minus e to the x plus 0. Well, e to the x minus e to the x is gone. See how we end up with x e to the x. See that? That's how we check it. You can check it, right? You make sure your integration by parts is correct if you wanted to. We won't check it every time, but that's how you're going to roll with that. So here's some common integrals using integration by parts and just kind of some tips. I think more than anything, it's kind of a little bit of trial and error initially. So let's go ahead and do this one. Now this one has a repeated integration by parts, so I'm going to have you guys try a different one actually than this one. Let's put this one to the test. So we're going to use the same approach. I'm going to say, well, I'm going to let dv be the more complicated portion that I still have a basic integration formula for. So I'm going to let it be. I'm going to go to the side and I'm going to let my dv be that e to the x dx. That's the first thing I'm going to try. And if I'm wrong with it, it doesn't work after a couple tries on this, then I'll switch it up and try something else, right? And so that means this would have to be my u, right? Because we're setting up the integration of u dv, right? That's what we're setting up, is uv minus the integration of v du, right? That's what we're setting up. So number 1, we had to find my dv and our u. We had to do that first, right? And then we'll come back to the formula, plugging it in. Right? All right, let's take the derivative here. So du dx, so u is x squared, du dx would be 2x, right? So du is 2x dx, right? Du dx is 2x, take the dx to the other side. Over here, we've got to integrate that. So the integration of 1 dv is just a v. Integration of e to the x is 1 over ln of e to the x. Again, don't worry about the plus c. We'll deal with that when we plug it into the integration by parts formula over here. All right, so the integration of u dv, which is the integration of x squared e to the x dx, is uv u is x squared, v is e to the x. X squared, v is e to the x. Minus the integration of v, and du now is 2x dx. 2x dx. And so we've got x squared e to the x minus, and I'm going to write the 2 in front, x e to the x dx. Okay. Now the problem is, I'm looking at that and I'm like, gosh dang, I thought I was getting somewhere, but I still don't have a way, I don't have some basic integration formula for that, do I? And so I'm going to have to repeat the process. I'm going to have to do integration by parts again. Okay. And if it doesn't work after I try it again, then switch up your u and your dv to the other one. Okay. But we already did x e to the x, right? So we know that integration by parts already works for this. We had already let dv be this part and u was that part, right? So let's go ahead, repeat the process. I'm going to let u be x and dv be e to the x dx. So du is 1 dx, and over here I have v equals 1 over ln of e to the x. And so here we have, let's go ahead and write this now. So I have the integration of x squared e to the x dx is x squared e to the x minus 2. And then we're applying, remember, u dv, the integration of u dv is uv minus the integration of v du. So that's what I'm going to put in right here. uv minus the integration of v du. And so I have uv minus the integration of v du. Well, du is just dx. And so we have the integration of x squared e to the x dx is x squared e to the x minus 2. I'm going to distribute the 2 through. And then now I'm going to go ahead and run the integration of e to the x, which is 1 over ln of e to the x, plus a constant. All right. And there's our answer. All right, so here, you know, if I'm picking, remember, I'm setting up u dv, right? So let's say I was like, oh, let me let this be dv, and so u is the x squared, right? Let's say I did that for a minute. Well, do I have a formula for the integration of the natural log? No, I don't. So I'm not going to pick that. That's not going to work for me, right? Bad choice. So I'm like, well, I can't do that. Scratch that idea. So how about we let the dv part then be x squared dx. That'll be my dv. And so this will be my u. So let's do that. Let u be the natural log, because I know that derivative of the natural log is 1 over x. Right? So our dv here is x squared dx, and we can do that. Right? We can take the integral of x squared. So the integral 1 with respect to v is 1v, and then we got x cubed over 3. All right, so it looks like we're set up. We can do this. So we have the integral of u, which is ln of x, is my u part. My dv part was actually x squared dx. That was my dv. Is uv, here's my u, here's my v, minus the integration of v. There's my v. And then my du, which is 1 over x dx. And so this ends up being x cubed over 3 ln of x minus, I'm going to put that 1/3 out front, and x cubed over x, of course, is x squared dx. So we got x cubed over 3 ln of x minus 1/3 x cubed over 3 plus a constant. So we got x cubed over 3 ln of x minus x cubed over 9 plus a constant. And that's the integration of So that brings us to a good u-try problem. You know, I said, hey, we don't have a formula for the natural log, right? The integration of the natural log. So why don't you try that? The reason we don't is because it's an integration by parts problem. So if you were to create the formula, do it with the technique. What is the integration of the natural log? Figure it out with integration by parts. Good time to pause this and then we'll show it. We're going to let our u be that ln because, you know, I can't let that be part of my dv because I don't have a basic integration formula for that. So let's go to the side and let u be the ln of x. And dv is just dx. So when we integrate that, which is if v equals x, when we take this derivative, we get 1 over x dx. So the integration of u dv, integration natural log x dx, is u times v minus the integration of v du. So now, if you want to add that to your formula sheet, now, because of integration by parts, we know how to integrate the natural log. Well, now we can do stuff like this with, we couldn't do before, right? We can find an area and use that technique if it wasn't solvable prior to today. So we know the area of this region. The area of the arc sine would be the integral of the arc sine. We're bounding it from 0 to 1, so we just want that area, right in there, from 0 to 1. So what we're going to do is we're going to let u be the arc sine, because I know that on my formula sheet I have that derivative. So this will be my u, and then my dv will just be the dx. So my v equals x. My du, so I look at my formula sheet, the derivative of the arc sine is 1 over the square root of 1 minus x squared. So this area from 0 to 1 of the arc sine becomes uv. So here's my u. There's my v minus the integration of v and du. Now, I know this is from 0 to 1, but I'm not quite there yet to do that, to apply my upper and lower limits on this. Because I get to this point and I'm like, oh, do I know how to integrate that? Well, I got to use u sub, right? I got to use u substitution. So I'm going to let u be the radicand there, 1 minus x squared. So du is negative 2x dx. So I need a negative 2, which means I got to offset it with a negative 1/2 here. So there's my du part, right? So I have x arc sine x plus 1/2. And then I'm taking u to the negative 1/2, right? I'm integrating u to the negative 1/2, which will be u to the 1/2, negative a half plus 1, 1/2, all over 1/2, which is times 2 over 1. So times 2 over 1. I'll put it right there. I'm integrating. Remember, this is what I was integrating. Right? So that becomes u to the 1/2. There's my u to the 1/2 all over that 1/2. In other words, times 2 over 1 on the end there. And this is all from 0 to 1. So I found the integral finally, but I gotta throw on my bounds, right, from 0 to 1 on this. I gotta apply the fundamental theorem of calculus. So let's clean this up a little bit. I got x, arc sine of x, and then a half times 2 over 1. That'll cancel. So I just have plus the square root of 1 minus x squared, but I'm going from 0 to 1. So we've got, let's plug the 1 in. 1 times the arc sine of 1 plus the square root of 1 minus 1 squared minus, now let's throw the 0 in, 0 times the arc sine of 0 plus the square root of 1 minus 0 squared. And so we've got the arc sine of 1. Now let me go down here for a minute. If the arc sine, what's the arc sine of 1? Let me set it equal to theta. If the arc sine of 1 is theta, then that means the sine of theta is 1. And remember, you cut off the sign between negative pi halves and pi halves, right? And so we're looking for the sine of what is 1. Well, we know what happens right there, right? Pi halves. So we know sine of pi halves is 1. In other words, the arc sine of 1 is theta, which is pi halves. The arc sine of 1 is pi halves. At least that's how I think about it. Okay? So over here, let me erase this. I'm making a mess of this. So we got this becomes 1 times pi halves plus the square root of 1 minus 1 squared, so it's plus 0, minus, well, 0 times anything is 0, and then plus the square root of 1. So we got pi halves minus 1. Or, what's pi halves? 1.57 something, so 1.57 minus 1.57, blah, blah, blah. All right, next one's a U-try problem. It's a good time to pause it and give this one a shot, and then we'll work it out. All right, so our area here, will be from 0 to 4 of this x e to the negative x dx. And so we're gonna let this be our dv, or we're gonna let this be our u right there. So let's let u be x. Let's let dv e to the negative x dx. Okay, so we know du is dx. Now the problem over here with e to the negative x is you actually got to use u substitution here. You actually have to let u be negative x, and bless you, du is negative 1 dx when you integrate this. So I need a negative 1 dx. So I got to put in a negative 1 and I got to offset it. So my v is, remember, there's my negative dx, there's my du. So I have e to the u du. And so my v is negative. Now I integrate e to the u, which is 1 over ln of e to the u. Well, my u is negative x. So be careful when you do that dv part, because you actually have to use u substitution to do that dv part, to integrate dv. Okay. All right, so what do we got? We got this area, which is the integration of u dv equals uv minus the integration of v du. And so our area is from 0 to 4, x e to the negative x. There's our u dv equals uv. So here's our u, here's our v, minus the integration of v, which is negative e to negative x, du, which is just dx. So we've got negative x e to the negative x plus e to the negative x dx. Looks like we got to use u sub again. So we're going to let u be that negative x. So du is negative dx. Negative dx, which means I got to throw in a negative out front to offset that. And so we got now we integrate. So 1 over ln of e to the u. Now, normally plus a constant, but in this case, we're going from 0 to 4, right? We finally integrated it by integration by parts. So we got to apply the limits here from a lower limit of 0 to an upper limit of 4, and then we got to throw that in. So we got negative 4 e to the negative 4 minus e to the negative 4 minus we got negative 4 over e to the x minus 1 over e to the 4. That's gone. And so we got negative times a negative is a positive, so plus 1. So we got negative 4 minus 1 all over e to the, whoops, that's supposed to be a 4 right there. Sorry about that. It's supposed to be a 4. Sorry. Negative 4 over e to the 4 minus 1 over e to the 4 is negative 5 over e to the 4 plus the 1. So in other words, the area is 1 minus 5 over e to the 4. Or that's like 0.9-ish something. All right, another one with a repeated integration by parts. So why don't you set that up, pause the video, and check your answer. All right, I'm going to go ahead and let that be my dv, the so-called more complicated portion, if you will, that I still have a basic integration formula for. And then I'll let that be my u. I'll let u be the x squared, dv be the sine x dx. Let's go ahead and integrate. We got v equals, we got negative cosine here, du equals 2x dx. So the integration of u dv, so the integration of u dv is u v, oops, minus the integration of v du. Okay, so here's where we're at now. We can't integrate x cosine x without running integration by parts again. And so you want to repeat the approach you had on the first one. In other words, on the first one, we let the u be the trig part. I'm sorry, the dv part be the trig part, right? So I'm going to do the same thing here. And so here's what we got. Negative x squared. Oops. Let me do that in blue. And then I'm going to put in my uv minus the integration of v du. Let me distribute that as well. And then I take the integration of the sine, which is negative cosine. So just note, you guys, be careful not to interchange the substitution in successive applications of that integration pipe part. So for example, in this red part over here, okay, if I had switched this and I had made in red here the second time I did it, and I went u being the cosine and the dv being like 2x, what happens is you're undoing the previous integration and you return to the original integral. So it just sends you in a circle. Okay, so just be leery of that when you're having some repeated applications of the integration by parts. Secant cubed. We're going to take a look now at it. This is called integration by parts with constant multiple of the original integral. And so this one's a little bit funny. You probably want to think about this as the secant times the secant squared. And that's because I have an integral formula for the secant squared. And I can also take the derivative of the secant, right? So that's what I'm going to do on this, is I'm going to let u be the secant. And I'm going to take that derivative, and so I get secant tangent. And then I'm going to go over here and I'm going to say, well, dv is secant squared. And I'm going to integrate that. I know I have a basic integration for the secant squared is just the tangent. So the integration of u dv becomes, so the integration of du dv is uv minus the integration of v du. And so the integration of the secant cubed becomes u times v minus the integration of v du, just secant tangent dx. Oops, I forgot my dx up there. So the integration of secant cubed so notice I have secant and I have tangent squared. Okay. Well, I can't integrate tangent squared. So if you remember sine squared plus cosine squared is 1. Right? My money formula, my Pythagorean identity, sine squared plus cosine squared is 1. Well, if I divided everybody by cosine squared, then I would have tangent squared plus 1 equals secant squared. In other words, the tangent squared is secant squared minus 1. And so I'm going to replace that tangent squared with secant squared minus 1 so that I can actually integrate this. And I'm going to go ahead and distribute this. So I got secant cubed x minus the secant of x. And then I'm going to split that up. So minus the secant cubed x. And then now this is going to both. So if I split this up, I have a minus, so that'll be a plus. That's secant, right? Now notice I was integrating, what I wanted to find out was what is the integral of the secant cubed? And over here, I have a secant cubed. You see that? And so that's a multiple of the original. And so I'm like, well, let me just add it to the other side, right? I can add this to the other side. And so what I have is 2 of these, 2 of what I want, which is the integral of secant cubed x dx. And let's see what we have over here on the right now. And then I look at my formula sheet because I can take the integral of the secant, and my formula sheet tells me it's 1/2. Oh no, I'm sorry. My formula sheet tells me it's the natural log of the absolute value of the secant plus tangent. Now we want the integral of secant cubed, right? So I just got to get rid of that 2 in front. So let's just divide this by 2. All of these divide by 2. Well, constant divided by 2 is still a constant, right? So the integral of the secant cubed is 1/2 the secant tangent plus 1/2 the natural log of the absolute value of secant plus tangent plus constant. So this next one is a good try it problem. I want you to try this one. It also has, it pops up that a constant multiple of the original. So go ahead and pause it and try it. I let that be my dv. I let that one be my u. So du would be ln e to the x. Again, ln e is just 1, so e to the x. So the integration of u dv is uv minus the integration of v du. So the integration of e to the x sin x is u v minus the integration of v du. Then we're going to do it again. So this will be our dv, that will be our u. So du is ln e to the x. V, integration of sines negative cosine. And so we've got minus uv minus the integration of v du. I'm going to distribute that. Let's see, positive times a positive, I'll make that positive there, but then I still got the negative in front of the cosine, so minus dx cosine x dx. And remember, we're integrating e to the x cosine x, so now I'm going to recognize, oh, that's the original. Let me take it over. So I happen to have 2 of these, e to the x cosine x, integral of e to the x cosine x dx equals. So we got e to the x sine x, c to the x cosine x. And now we just got to divide, I should say plus a c. Divide everything by 2. And no, you could have let u be cosine and dv be e to the x dx and got there as well. All right, how about a volume now that we couldn't do before without integration by parts? So notice I do have the picture of this. We're taking e to the negative x, right? So we taking e to the x, revolve it about the y-axis there, right? Reflection about the y-axis, so we've got this e to the negative x right there. We're going to bound it from 0 to 1, 0 to 1 there, and we're going to do it about the y-axis. And so we're going to go ahead and slice this. The best option here would be the shell method, the cylindrical shell. So we'll slice this thing parallel to that y-axis, and we'll spin it as I've kind of tried to show here, right? We spin in all those shells. And so if you remember, our shell method is 2 pi shell radius times shell height from A to B. So in this case, we got 2 pi. We're going from an x value of 0 to an x value of 1. Our shell radius, there's our radius, which is just out x amount. There's our shell radius. And our height is the functional value in this case, e to the negative x. And so our volume is just 2 pi x e to the negative x dx from 0 to 1. And so we're going to go ahead and let dv be that e to the negative x, and we're going to let that u be x. Now, in order to integrate this, you're going to have to let u be negative x. So du is negative dx. Oh gosh, what did I do? Du is negative dx. So I need a negative dx, which means I got to offset it. So my v is negative e to the u du. So negative, then I integrate e to u, which is 1 over ln of e to the u. So there's our v. So v is negative 1 over e to the x. Over here, I take the derivative, du is 1 dx. And so let's go back to our volume now. So we got 2 pi, and this integration of u dv becomes uv minus the integration of v du. Maybe I should make those brackets. Probably be a little better. And now we're going to go ahead and integrate this by letting u be negative x. So du is negative dx again, the negative in. And so we've got 1 over ln of e to the u plus a constant. Right. And then remember, this is from, right? We did have lower bounds, so I should not have that plus constant. Sorry about that. Screwed that up. That's from, where are we going? 0 to 1. 0 to 1. So we got 2 pi, we got negative 1 over e, and then this is minus, you know what, let me rewrite this actually. So we got negative 1 over e minus 1 over e. I got negative 2 over e. And I got 0 minus 1 plus 2 pi. So I got 2 pi, negative 2 over e plus 2 pi, or 2 pi times 1. So if I take a 2 pi out, I have negative 2 over e plus 1, or 1 minus 2 over e. Or, yeah, I guess you could write it as 2 pi minus 4 pi over e is the same thing. Either of those work. Is a decimal. Well, I hope that gets you started on integration by parts. Thanks so much for watching. See you next time.